happens dynamically here. We want to have a simple look at a boost converter. Simple example. Let's have a look at the boost topology. We are interested here in the switch node to see our voltages. And what happens? When we close the switch, we got ground potential reflected here. We force a current across the inductor, and we got input voltage across the inductor. Now, when we open the switch, by inductance law, the voltage across the inductor turns. Now we are adding the inductor voltage to the input voltage, and basically means boosting our voltage. And by adding the inductor voltage to the input voltage, our rectifier starts to conduct, and we are delivering energy to the output capacitor and of course to our load. Let's have a look on voltages and current. Of course, just taking a duty cycle roughly around 50%, pretty easy for me. So I could say that this duty cycle, that this is roughly my input voltage, and this is my inductor voltage. What happens with the current? Well, let's have a look here at the current. When we close the switch, we force a current across the inductor. When we close the switch, we force the current across the inductor. And when we open the switch, the current is driven to the output of our power supply. Basically, that's your current waveform. But there is a main difference to buck topology. At the buck topology, the output current is continuous. At the boost topology, flyback topology, the output current is discontinuous. Basically, that's the current delivered to your output. It's averaged, of course, means your DC current will be roughly around here. Your DC output current, because very simple, roughly this area has to match into that area. What I talk now is just the boost topology in steady state. Now let's have a look what happens dynamically. Our load resistance drops. Basically, the load says, give me more current. What happens now dynamically? Listen to me. Dynamically, before we can deliver more energy to the output, we have to store more energy in the air gap of the inductor. Means we have to increase the duty cycle. And to increase the duty cycle in a fixed frequency system means we increase the on time, but on the other hand, we decrease the off time. If we decrease the off time, the result is that we get less energy to the output of our power supply. And now remember, we had a transient. The load required more current, more energy. And what we are doing in the very first moment, we are delivering less energy. So in the very first moment, dynamically, we are doing exactly the opposite what our load expects us to do. And this behavior is in all power supplies, delivering energy to the output when the switch is open and if you are in continuous conduction mode. What I discussed you now on in the time domain, in frequency domain, this behavior is called the right half plane zero. There is a transition in duty cycle. First, in case of transient, you increase the duty cycle, then you decrease the duty cycle again. This is some kind of swing, and you have to attenuate, you have to dampen that swing. If you don't do this, your power supply will be unstable. Typically, the right half plane zero. The right half plane zero is dominated by the magnetizing inductance, by the duty cycle, and by the load resistance. We could calculate this by hand. We got several equations on this, or you use CI power stage designer version of 3.0. There, the software itself calculates the right half plane zero to you. And I said, the right half plane zero depends on output current for load resistance. Means at biggest duty cycle, so lowest input voltage, and a high magnetizing inductance, the right half plane zero might be very low. Could be in a range, typically range is 10 kilohertz to 100 kilohertz. And the rule of thumb is that the bandwidth of your power supply, if you do it very conservative, will end up around 10% of your right half plane zero. If you do it more often, with more dynamically, maybe 20%. So if your right half plane zero is at 10 kilohertz worst case, your bandwidth is 1 kilohertz, maybe 2 kilohertz. The crossover frequency is limited by your right half plane zero. And there is one thing to know. You are not able to compensate the right half plane zero by any poles and zeros you put to the arrow amplifier. That's important to know. Another question that I'm going to see here, why the flight back topology in discontinuous conduction mode is not limited by the right half plane 0, could be explained very simply. Please have a look. If we are in discontinuous mode, we're switching on. Our current waveform looks basically like this. And if we are in discontinuous mode, pretty simple, you are able